So this brings us to Kepler's laws. So Kepler's first law tells us that all planets move in elliptical orbits like this one with the sun at one focus. So an ellipse has two focuses and the sun which it's orbiting around needs to be at one of these. So Kepler's second law tells us that a line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. That is, the rate dA dt at which it sweeps out an area is constant. Okay, so let's see what this actually means by having a look at a simulation, and then we'll go ahead and actually prove it. So this is a nice simulation showing Kepler's second law. So we'll start sweeping, and it's showing the areas which are traced out in equal times. So you can see here we have a wide but shorter triangle, and over here there's a much longer but less wide triangle. So you can see how the satellite is moving slower when it's further from the sun, and then when it gets round to being closer to the sun, it goes very quickly. So let's prove this. Let's consider this triangle which the satellite sweeps out as it moves through the angle d theta. Well, we know the formula for the area of a triangle is just half the base times the height. So the area of this small triangle is given by a half. Now this length here is the radius, and then the length of our triangle is the arc length, which is r d theta. So we've got a half r squared d theta. Now, what Kepler's second law is telling us about is the rate of change of this area. So to get that, we're going to have to divide by dt. So we've got dA dt is equal to, now the radius is changing very, very slowly. So we can choose d theta to be small enough that the radius is constant. So then we've got a half r squared d theta dt, and we know what d theta dt is. It's omega, the angular velocity. So this is a half r squared omega. Now, r squared omega should vaguely remind you of moments of inertia. We've got that the total angular momentum is given by I omega, and the angular momentum is conserved. So if we assume angular momentum is conserved, then I omega is equal to a constant, and we've just got a planet, a point mass moving here. So I is given by mr squared omega. So we can say, well, rearranging this, we've got this is equal to L, our angular momentum. We can replace r squared omega with L on m. So dA dt is equal to a half L on m. Now the mass of the planet is definitely not changing, and as long as we assume that the angular momentum is conserved and isn't changing either, then we can see that dA dt is equal to a constant. So we've now proved Kepler's second law. So this brings us to Kepler's third law, which tells us that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. So we've got this equation here. This one's not too hard to show, because when we consider the satellite orbiting around the planet, we know that it's undergoing circular motion. So the resultant force acting on the planet is just the centripetal force, which is given by mv squared on r. We also know what force is causing this resultant force. The only force between the satellite and the planet is the gravitational force. So this is equal to gmm over r squared. So we can cancel out one of these r's and the little m, which is the mass of the satellite. So we've still got the mass of the planet there. And so now we've got v squared is equal to gm on r. Now we know for the planet that the velocity is given by the distance divided by the time, which is 2 pi r over the period, which is t, and this is a velocity squared. So this is the velocity in here, and we're squaring it. So looking at this part of the formula, we can write, well, gm on r is equal to 4 pi squared r squared on t squared, which we can rearrange to say, well, t squared is equal to 4 pi squared, and then we've got an r squared here times an r here, so that's r cubed, divided by gm. And that is the formula which is written just here. So the square of the period is proportional to the cube of the radius of the orbit. So to practice using this, homework set 3 for 1121, try question 12, or 16 if you're in higher physics.